Hello everyone, today we're gonna start with unit number 2 streams, and this is the first lesson that treats the heat recovery basics between two streams. The main objective of heat integration is to find an optimal set of thermal contacts that allow the process to work with the minimum heating and cooling, or being an optimal HEN, an optimal heat exchanger network, as we saw with different criteria. This problem has two aspects: the condition for one or for each contact between two streams and the different sets of contacts. It's important to understand that these are problems of a different nature, studying the contact in one pair or trying different sets of different pair of streams. In this unit, two streams, we're gonna tackle the variables and conditions that influence a single thermal contact, one pair, between two streams. And for that, we're gonna use a simple heat integration project. As simple as that. One hot and one cold stream in a process plant. Here you see a hot stream going out the reactor that must be cooled before arriving to a column, and a cold stream coming from battery limits that must be heated before to arrive some process vessels. The question is, how much heat can we recover from hot to cold? The condition is that supply and target temperature, starting and final temperature, must be maintained. With what happens in the middle is our business, but start and end must be respected. And in the middle, what we want is to pass heat from the hot to the cold stream. Then, a new heat exchanger is needed. We must pay for it. There will be an investment. The heating and cooling heat flows or duties change, decreasing, even disappearing. You see, this heating duty will be replaced for this other, and that will be less than the original one. And the same thing for the cooling duty, that will be reduced. In fact, savings in heating and cooling are the same, must be the same. Gonna try to quantify a bit the thing. We are doing analysis, not design. This is a balance, a heat balance. But still, we can put some numbers in it. Think in a conceptual countercurrent heat exchanger, where the hot stream here passes heat to the cold stream here. Probably the heat that can take out the hot stream and arrive to the cold one is not exactly what the hot stream needs, and then some cooling, additional cooling will be needed. And the same thing for the cold stream, some additional heating will be needed. The heat exchanger duty equals the enthalpy flow leaving the hot stream, and is the same, this question of the first law, that reaches the cold stream. This heat must be the same. Here you can see the equation for sensible heat, if the change is just sensible heat. The same thing can be put for condensing or evaporating. This for the first law, and for the second, for the heat to flow spontaneously, the gradients on the hot side, this side, the difference between these two temperatures, and the cold side also must be greater than 0. And for real contact, This gradient must be finite. 10 Celsius, 5 Celsius, no 0, that's 0, because 0 will give us an infinite heat transfer area. As you can imagine, the extension of those gradients are crucial when calculating the heat recovery possibilities.